Hi, my name is Matthew, and I'll be teaching you a quick lesson on what probability is and how you can calculate the probability of two independent events. Let's first define what probability is. In mathematics, probability means a likelihood of an event happening. Higher probability means that the event is very likely to happen, and low probability means that the event is less likely to happen. Probability could be as small as 0, meaning that it has no chance of happening, and it could be as big as 1, meaning that it has a 100% chance of happening. Typically, we use fractions to express probability, but it is acceptable to use both decimals or percentage. Here we have the formula that calculates the probability of an event happening. It is number of wanted outcomes over total number of possible outcomes. This will make more sense if we use an example. Here we have a die, and the question asks, what is the probability of rolling 3 from a 6-sided die? We would express this as P bracket 3. P represents probability, and 3 represents what we want. So what is the probability of rolling 3 from a 6-sided die? How many possible outcomes do we have from rolling a die? Well, we could have a number from 1 to 6, right? We could get 1, we could get 2, we could get 3, and so on. So we have 6 total possible outcomes, but we want to roll 3. And how many 3s do we have on a die? Only 1. And that is why the probability of rolling 3 from 6-sided die is 1 over 6. How about the probability of rolling an even number? Again, what is the total number of possible outcomes? We have 6. We could get any number from 1 to 6 again. But how many even numbers do we have on a die? There are 3 of them, 2, 4, and 6. That's why we put 3 on top, because that is the number of wanted outcomes. And we simplify this by dividing both top and bottom by the greatest common factor, which is 3 in this case, and that is 1 and that is 2, so 1 over 2. There are 2 ways of displaying all possible outcomes. This is especially important when we have 2 or more events. First way is called a tree diagram, and I'll be using a scenario of flipping a coin and rolling a die. And we're going to solve that P bracket T comma 4 at the end. First, we are flipping a coin, and we have 2 possible outcomes. We could either get a head or a tail, and afterwards, we're rolling a die, and we could roll any number from 1 to 6, and that's why we have our second event, and we have 6 possible outcomes after each of the first event. When I taught this in a high school math class, some people had trouble interpreting this diagram. So for example, let's talk about this. What does that mean? It means that we're first flipping head from a coin, and then we're rolling 4 from a die. What about here? That represents a case when we flip tail from the coin and we're getting 1 from the die. And if I write these using a mathematical notation, this would be h comma 4, meaning that I'm flipping head and then I'm getting 4, and this will be t comma 1. And now, what is the probability of t comma 4? So first we are flipping tail and then we're getting 4. How many total possible outcomes do we have? We have 12, right? Because we have 6 here and we have another 6. So in total we have 12. But how many of T4s do we have from here? We only have 1 of them here. So what is the probability of flipping tail and then getting 4? 1 over 12. And we could display the same possible outcomes using a table instead. We are flipping a coin and rolling a die as before. And when we use a table, we first draw out the grid and then we write coin. And there are 2 possible outcomes, head and tail. And then after, we're rolling a die. And we have 6 possible outcomes, right? So those 2 represent a case when we get 1 from a die. And this is 2, 3, 4, 5, 6. And this is how we can display all possible outcomes. To use the same example, probability of calculating t comma 4, How many possible outcomes do we have? We have 6 possible outcomes here, another 6. So in total, we have 12 over how many T4s do we have from this table? Only 1. And that's why our answer is 1 over 12, just like before. Let's solve another problem. 1 green and 1 red dice are rolled. What is the probability of their sum being greater than 10? Let's use a table to show all possible outcomes. And the reason that I chose table is because it is easier to see the two results side by side rather than seeing one above the other. So first, we're rolling a green die and we have 6 possible cases, and then we have a red die and we're rolling 1, 2, 3, 4, 5, 6. So now we're calculating probability of sum greater than 10, that is equal to how many total possible outcomes we have. You could count these one by one, but if you think about it, there are 6 over here and there are another 6. So 6 times 6, we have 36 possible outcomes. And how many cases do we have when the sum of the two results is greater than 10? We have 3. 1, 2, 3, right? The sum of 5 and 6 is 11. That's the same, and this is 12. So we put 3 in the numerator. And we simplify this by dividing both numerator and denominator by the same number. In this case, it'll be 3. And we have 1 and 12. So 1 over 12. And that's our answer. And now let's talk about independent events. What are the independent events? We call events independent when the outcome of those events do not affect each other. For example, when you flip a coin and you roll a die afterwards, does the result of flipping a coin affect rolling a die? For example, if you get head, is it more likely to get 6 from a die? No, it doesn't, right? Whatever you get from a coin, it does not affect the probability of rolling a die. So that's why they are independent events. But what about this case? Drawing out cards from a deck without putting them back. Let's say you're drawing 2 cards from a deck. Does the result of your first draw affect the probability of the second draw? Yes, it could. Because, for example, if you draw ace from a deck, now the deck has 1 less ace, meaning on your second draw, you are less likely to get another ace. The result of the first draw affects the probability of your second draw. So that's why drawing out cards from a deck without putting them back are not independent events, but dependent events. But if you remove this word, without, let's say that you're putting the cards back in the deck and you're shuffling it every time. Does what you get from the first affect the probability of what you're getting from the second? No, it does not, because you're putting it back and you're shuffling every time. What you got from a previous draw do not affect your second draw. And that makes this event independent. But for this video, we will assume that all events are independent. Let's take a look at this question. A coin is flipped and a spinner, which has 4 sections, is spun. How many possible outcomes are there? We're not calculating the probability, but for now, we're only counting total number of possible outcomes. Let's use a tree diagram. First, you're flipping a coin and you have 2 possible outcomes. And afterwards, you're spinning a spinner and you have 4 each under the outcome of flipping a coin. How many possible outcomes do we have in total? We have 1, 2, 3, 4, 5, 6, 7, 8. So our answer is 8. But another way of thinking about it is that we have 2 possible outcomes from flipping a coin. And then from a spinner, we could have 4 possible outcomes. So in total, we have 8 possible outcomes. So when you have multiple independent events, all you have to do is to multiply the possible outcomes of each of them, and you get the total number of possible outcomes. And this principle stays the same even if you add the third event. So in this case, coin is flipped, a spinner is spun, which is the same as the previous question. But now we also have a die, 4-sided. How many possible outcomes are there? I'll be using a tree diagram to show you all possible outcomes. But using the principle that we learned from the previous slide, 2 from flipping a coin 4 possible outcomes from the spinner, and we have another 4 from rolling a 4-sided die. And 2 times 4 is 8, times 4 is 32. And here is a tree diagram. So first, you have 2 possible outcomes, head or tail, and you could get 4 different colors from the spinner, and you could roll any number from 1 to 4 from the die. How many of the possible outcomes do we have? Well, we have 4, and we have 1, 2, 3, 4 of them, so that's 4 times 4, which is 16, and we have the same exact set on the other side. So we have 16 times 2, so that is 32. And I hope you noticed, but the way that I just counted them was 4 times 4 times 2, which is exactly the same as our 2 times 4 times 4. So when you're counting the total number of possible outcomes, doesn't matter how many events you have, all you have to do is to multiply the number of each possible outcomes. But now, let's actually calculate the probability. A spinner of 3 sections is spun and a coin is flipped. What is the probability of spinning 3 from the spinner and getting tail from the coin? If I were to use a tree diagram again, we have 3 possible outcomes. On each of them, we could get either head or tail. What we want is 3 and tail. Out of 6 possible outcomes, we only want one of them. So that's 1 over 6. But here is another way of thinking about it. What is the probability of getting 3 from the spinner? Out of 1 to 3 options, we only want one of them. 1 over 3. And what is the probability of getting tail from the coin? Well, we could either get head or tail, but we only want tail, so that's 1 over 2. And when you multiply them, you get 1 over 6, which is same as using the tree diagram. When events are independent, we can calculate the probability of an event happening by multiplying the probability of the first outcome that we want by the probability of the outcome that we want from the second event. And if you multiply them, we get the probability of what we want. This will make more sense as we solve the last question. There are 2 red and 1 blue marble in the first bag and 1 yellow and 1 green marble in the second bag. What is the probability of getting red from the first bag and getting yellow from the second bag? Let's draw a diagram to visualize what we have. So we have in our first bag 2 red and 1 blue, and in our second bag we have 1 yellow and 1 green. Let's first calculate and then use a tree diagram to show that we have the right answer. What is the probability of getting red marble from the first bag? Out of 3 possible marbles that we can pick, 2 of them are red, and in our second bag we have 2 marbles and only 1 of them is yellow. So if we multiply them, the probability of getting red and yellow is 2 over 6. And if we simplify by dividing both top and bottom by 2, we get 1 over 3. And now let's check using a tree diagram. In the first bag, we have 3 possible outcomes. One is picking the first red marble, or we could pick a different red marble, or we can pick the blue one. And afterwards, we're going to pick a marble from the second bag, and we could either get yellow or green, right? And the probability of picking red and yellow is picking red and yellow. Picking red and yellow. Out of 6 possible outcomes, how many of wanted outcomes do we have? 2. So that makes it 2 over 6. And if we simplify, they become 1 over 3, just like before. In summary, if you have multiple independent events, you can calculate the probability by multiplying the probability of getting what we want from the first event by the probability of what we want from the next event. Hopefully you found this video helpful. If you did, please hit that like button and subscribe, and check out my other videos as well. I'm Matthew, and I'll see you in the next video. Bye!